they need some background, but we don't need very rigorous quantum mechanics, but better to remind you something, right? So
that'll make for a great recording.
yeah. I think you all took 621 last year. Yeah. So nobody's taking quantum this semester, right? So next semester you'll be taking 622. No, you did. Yeah, finished. You guys are almost done now. You're only taking 625, right?
Yeah.
Yeah. Yeah, they are second year PhD programs. Sometimes it's hard to find the place, right, from somebody outside.
Yeah. Feels good.
Yeah.
Oh, qualifier. That's your stat rank. Let's spend like 3 solid hours just squatting PLC. I have like 2 problems to show, but I'm working on like 5 others. So Thursday, we'll do it again. I'm somewhat organized.
I just started doing study and yeah.
It's okay. I feel a lot better than V cross B F.
Okay, let's get
we
started.
should discuss.
So this is physics 525 solid state physics, right? So you can see I have given all my information. So I have listed both my offices. I have one in Ernst Hall and here in natural science. So I have office hours Monday, Wednesday during this time, but you can always come and see me anytime. You can find me. So for this one, I have textbooks. This is Charles Kittle, very classical solid state physics book, and also Ashcroft and Mermin, that's a little higher level. But I don't want you to really buy this book, so I post all the lectures in the blackboard, so you can read that one. So, but if you need additional information, I encourage you to read these textbooks. So, but everything you need to know, I have it in the PowerPoint presentations. So here we mostly talk about physics of solids, nothing more like any polymers or other thing, mostly about solid state materials, semiconductors, metals, and then we go to more advanced topics like magnetism, superconductivity, and things like that. Did anybody read recent? There was a big hype about new room temperature superconductor.
I read something online for that.
So that turned out to be wrong.
Oh yeah.
Yeah.
I didn't know it was real or not.
Yeah. But it spurred a lot of interest in the scientific community.
Do you think it's possible?
I'm sure it's possible, but it will require more, yeah. Because there are materials like this topological insulators, those kind of things are, but they might need very high magnetic fields and things like that. But in ambient condition, it will be tough. Yeah. So here in this class, I just want everybody to learn. So that I'm not going to let's just put pressure on you. So to have some fun and learn from this class, that's the whole idea. For that reason, I'm not going to give you like in-class exam or anything. These problems very hard to do within this 2 hours, right? So, but I really want you to do this homework. I give homework every week, so you can come and talk to me, and you can discuss among yourselves homework. That's how you learn, right? So homework I give every week, but I usually assign homework on Thursday. For example, I will give the first homework in 2 days, right? So that will be due next Thursday. So you have entire weekend and the entire week, right? So you have enough time to work on the homework. So please work together. If you have any issue, come and talk to me. I will give some hints. So I think that way you learn better. For example, you want to calculate the band structure kind of things. It needs little work, right? So that you can spend time and do that. So this every week I will give you homework. They are not very difficult, so you have all week to work on that. So then the exams are also pretty much like homework. So only difference is I give the exam on a Tuesday, then it will be due on Thursday, because it's more like, exams are much simpler than homework. It's something that I give you in the class, right? So, but if I give in the class, it's a lot of stress and a lot of pressure, right? But here, because of that, I will give you 2 days, go home and work on that. But that one, I don't want you to discuss each other. That has to be done independently. You can refer to books or anything, that's fine, but please do independently. So that means tests are much simpler. That's something you will do in the class, but here you have 2 days to do that. So I give on Tuesday, it will be due on Thursday. You have 2 nights, right, to work on that one. So that's pretty much it. Then at the end, I will give about maybe 10-15 topics, so with some current interest. So you can write a term paper, like 4 to 5 page paper, so that you can refer to new literature and write a paper, that's all. So usually you have homework, you have test also like homework, right? So when I give the test, I don't give a homework for that week, so that you can work on the test, right? So then at the end of the semester, you write this paper. So it's like 4 to 5 pages. It doesn't have to be very detailed, but I want you to connect in that paper some topic you learned in this class. That's what I want to see, how you can apply that your knowledge to that topic I am proposing to you. So that's basically, it's only 4 or 5 pages, it's nothing much. Maybe some physics, right, some solid state physics concept you learned here, so include in that paper. That's pretty much all. So then this is just for the formality, right? Yeah. So I don't expect anybody to get anything less than A in this class. So if you do homework, and so that's how it was in the past. So basically, in this class, we are going to talk about mostly the crystal structure, right? Periodic crystals. So then some symmetry groups. Actually, we start with the chemical bondings. Then talk about the reciprocal space and diffraction. Then we're going to talk about something called the lattice dynamics. That's the phonons, right? How the heat is transported by. So then thermal properties, then electrical properties, then some band structures, then something called the tight binding approximation. Then mostly talk about in detail semiconductors, magnetism, and superconductivity. This is the, I think, foundation of what you learn here to use in, say, I think you will be working mostly on semiconductors, right? Even the perovskites and things like that.
No, I work on thermal batteries.
Oh, thermal batteries, okay. Yeah. So even that one you need to have some band structure, and yeah. Actually, that's very interesting, because I work in physics and also in the energy storage theme, right? So we have the same concept, but we use different words. That's the thing. Like here we talk about the Fermi energy, then chemical engineering they talk about the chemical potential. We talk about this valence band, conduction band, they talk about this HOMO-LOMO gap, and so it's the same thing but different language. Other than that, the physics is the same.
Do you interchange between the two when you talk to?
No, mostly I will stick with the physics notation, but you can connect it with the chemical engineering. So these are the, this is how the structure is going to be. In the first week, that means today and Thursday, right? I will give some little introduction for the quantum mechanics, especially for people from outside physics. So then I talk about the interatomic forces and the coherence and the cohesive energy, things like that. Then after, next week is mostly going to talk about crystal structures and go on, so you can see how it is going to be. At the end we talk about semiconductor devices. Semiconductor devices include things like solar cells, photodiodes and photo detectors and all the transistors and everything. Then superconductors and the magnetism. So we'll end with these things. So I have the dates for the test also here, right? So these are all Tuesdays. So if I give the test on the September 19th, that will be due September 21st, right? It's on Thursday. Okay, so that's pretty much all. So like I said, please relax and enjoy this class and learn as much as possible. I know some people, when they come to the class, they are under pressure. So this is completely different. So I just want you to relax and learn. That's the whole idea of this class. Okay, any question about the syllabus? Homework or anything? So you will see the first homework this Thursday. So then you will be working in the weekend, or because I understand all of this of you are taking other classes, right?
Yeah.
So this is not the only class you are taking. So we have homework in those classes, and
we also want to pass qualifiers.
oh yeah, that's another thing, right? Yeah.
Before it's all
So,
worthless.
2 weeks, right? 9, yeah.
Yeah.
That's the first thing to do, right?
So,
Okay, so unless you have any other questions, we can go ahead and get started, right? Yeah, today and tomorrow mostly we are going to talk about introduction to quantum mechanics. So I don't know whether you are familiar. So quantum mechanics was actually developed because there were certain concepts that before quantum mechanics it was all classical mechanics, right? So people tried to explain a lot of things using the old classical mechanics. There were at least 3 or 4 concepts couldn't be explained from the classical mechanics. Right? One of them was the black body radiation. So another one was photoelectric effect, right? So that also they couldn't explain from the classical theory. So then Compton effect was another one. And most importantly, the wave-particle duality, and also the quantization of some energy states, right? Those things couldn't be explained from the classical mechanics. So first, I think biggest issue was, so this is what classical theory predicted for intensity of emitted light from a black body. So black body means typically, if we have a perfect black body, means it can emit light at every wavelength, right? So that also it can absorb entire radiation by that black body. There are no reflections. If this is my black body, if some radiation comes, it will be perfectly absorbed. No, nothing is reflecting back. So that means if I consider this function alpha for every wavelength, so your alpha will be 1. That means everything comes will be absorbed, and also it will emit radiation for every frequency, from ultraviolet to so infrared or whatever. So entire range it will absorb. So classical theory, if you look at this one, so look at this one. So when you decrease the wavelength, you can see that the emitted intensity is going to continuously go up. So that means if you get to lowest wavelength, it will emit infinite amount of radiation, right? So we know that's not true. So that is actually called the ultraviolet catastrophe, right? So that's the first thing I think people were puzzled by this one, why this theory was not accounting for this one. But people already knew this spectrum. So everybody should know the black body spectrum, right? So if you heat some object, if you measure the intensity, this is how it should. That people knew this experimental result. But theory only predicted this part. It's quite close to this part, right? But nothing going down. So when you assume this theory, so this is the Rayleigh gene, right? So he assumed this every at the given temperature, it emits some average energy of kBT. That's the thermal energy, right? So it was assumed when you derive this theory. That's how if you do this one, you get this actually this is close to 1 over lambda 4 kind of dependence here with respect to lambda. So then nobody could explain this one. So then Max Planck, so he came up with this idea. He said, no, it's not just average energy is not this one. You have this different frequencies. They emit some energy. That average energy actually, these frequencies are distributed in some kind of Maxwell-Boltzmann distribution. So we are going to learn about these distribution functions later. We are going to talk about Maxwell Boltzmann distribution, then Fermi-Dirac distribution, and all these things. We're going to talk about that. He said this average energy is kBT. So this is not light. So he said this light emitted by this one, they are actually packets of this energy, right? They have some discrete energy. So he said it has energy of h nu. So h is the Planck constant, so nu is the frequency. So then the average energy actually, they are distributed in a Maxwell-Boltzmann Maxwell-Boltzmann kind of distribution. Then the average energy is really this h nu divided by this this function is given by, you don't want to know. We are going to do this one later when you talk about the phonons. So this is the energy per one, we call the wave packet, right? So then total energy is going to be distributed by this function, this one. So you can see this is pretty much different from this one, right? But if you take some for smaller frequencies, this function is going to be very small, right? So then we know how to expand Ex, typically 1 plus x kind of thing. That means Ex minus 1 is simply x. So in that case, you can make the assumption h nu divided by, so you can see this 1, this 1 cancel, you get only h nu over kBT, right? So you can see h nu cancel, this getting kBT. So that is, this boils down to this value for small frequencies, so very high temperatures. But this was the problem. So when they derived this function, they assume this very simple average energy. But Planck came and said, no, they are emitted by this wave packet, but that wave packet also, they are, the frequencies are distributed with some statistical distribution given by this one. So if you do this one, you can get exactly this curve. So that's the very first demonstration of the success of the quantum mechanics. Right? Then people started believing in. So that's why this photon, we call these energy packets as photons. So these are more like discrete. So if you take a black body like this, right? Suppose this is at temperature T. So we know this will emit radiation at every frequency nu. So that means you can assume that frequency has some wavelength, right? You can have something like this, or you can have something like this, or you can have more like this. So actually this intensity is sum of all these wavelengths or frequencies. So that's what I put for a given temperature. So that means you can consider that average energy, not this one, is a sum of all that frequencies, right? That's what usually you write, you know how to write a wave function, right? EIKX. So you have to take the sum of all these wavelengths. K is basically this 2 pi over lambda. Then the energy for each frequency is given by simply h nu. So this is very similar to, everybody remember the simple harmonic oscillator? So if you take a simple harmonic oscillator, something your free potential is something like half k squared. So they have these energies given by this kind of energy, right? H nu. So actually h cos omega, whatever, that is the oscillator frequency. So this is somewhat similar to so this is also quantized, right? So I'm going to talk about quantization later. Simple harmonic oscillator is basically, you have quantized energy states, right? So this is basically proportional to 1 over n squared, right? So if you calculate, no sorry, about to n, so your energy, yeah. So don't worry about this half. Actually, half is mostly what we call the 0 point motion, right? Even 0 temperature, you have some kind of 0 point. So then the energy of this photon, pH means photons. Sometimes later we are going to talk about something called photons. We have to be careful with those things. Photons versus phonons. You have to be careful. Here we are talking about photons, right? These are light packets. So phonons means some lattice vibration. So if you take a crystal, so they are actually not really in fixed position. So they are at fixed position at T equals 0 Kelvin. At any finite temperature, they are moving back and forth. That means we can represent that as a wave, right? So that we call a phonon wave. So here we are talking about photons. So they have energy, h nu. Then we can define the momentum, right? So I don't know whether you are familiar with, in relativistic situation, in general Einstein's theory says your total energy is given by E squared is given by, this is the free energy. So if it is moving at certain velocity, so your mass is changing, right? So photons are massless, no mass for photons. That means this term is 0. That means your E is given by simply P times C. So photons, your momentum is given by this energy given by C. Energy means h nu, right? H nu divided by C. That's what this one is. That's a photon energy. So we'll talk about this one later. So actually, the photons we can consider as massless. Actually, in terms of the spin, these are bosons, right? This is spin 1. So the velocity is velocity of light, right? C. So actually, when you derive that intensity using, remember I talk about this, the Maxwell-Boltzmann distribution, then you can find that energy is given by this function. I'm not going to derive this one because I do the same derivation when you calculate the heat capacity for the thermal heat capacity. So this is exactly same derivations. For that reason, I'm not going to do right here. So, but we'll do it in a different situation. So this is the energy density per unit photon energy. So for a given t, you can see it depends on t. So if you plot this one, this u versus energy, you see that the curve, not this one, right? So you can see, can account for that entire black body curve. But there we showed that function not with energy for lambda, right? So that means we can easily convert this function to lambda, because we know the relationship E is given by h nu. Nu is basically, yeah, you can write here. So frequency is basically your C over lambda, right? So that means you know how to represent this E in terms of lambda. So if you do that one, you can easily show the relationship, this U, not in terms of E, in terms of lambda, by using this simply E is hc over lambda, right? This is h, t is, yeah, if you do this one, you can find d, E is hc over lambda. So then dE over d lambda is basically minus hc over lambda square, right? So you just plug in E everywhere and you get now U in terms of lambda. So you can see this is, if you plot, this is what you get your curve, not this one. This is the bad one, right? So now you can see if you go to like high, for high wavelength, so then what happens? If you go to high wavelength or high temperature, this term becomes smaller, right? So then again I can expand this one using exponential, this Ex equals 1 plus x, then Ex minus 1, you can write as this one. Then what you get here? Here you have that 1 over lambda 5. This one I can write as simply hc over lambda kBt, right? So you can see this lambda, one of them cancel, you get exactly 1 over lambda 4. So that is true, right? For higher lambda, yeah, sorry. So this is higher lambda, right? Higher lambda means this part is smaller. So then that case, this one is correct. Everything is working out. So then also you can, yeah, that's what this one is. So another thing, I don't know how much people are familiar with this unit. Are you familiar with the unit EV, electron volts? So typically we are talking about even like band gaps and everything, we write in terms of electron volts. Electron volts means if you take one electronic charge, if you have it in a 1 volt potential difference, what kind of energy, right? Energy is given by charge times voltage. So that means 1 electron means 1.6 times 10 to the power minus 19 coulombs, right? Times 1 volt. So this becomes joule. So this means really 1.6 times 10 to the power minus 19 joules. This is what 1 electron volt means. So then there's a very important conversion, how to convert electron volts to the wavelength. So this everybody should know this one, this formula. If you want something in electron volts, this should be equal to 1.24 divided by lambda in micrometers. This is something, if I give you something in micrometers, you can immediately tell that is in electron volts. You just 1.24 divided by lambda. You can easily solve this one, right? So E is given by h c over lambda. So we know h, we know c, that's how this one is coming here. So it's very important to remember this one. This is coming from this 1.24. It's like 39 something. 1.24 is a good estimate to do. So like now here, you can say what is the electron volts for this one. So this is in nanometers, right? That means in micrometer, that's 1, right? That means this means exactly that is 1.24 electron volts, right? So this is lambda is 1000 nanometer means 1 micrometer, right? So that means you divide by 1.24 divided by 1 means in electron volt that is 1.24, right? So this is exactly 1.24 electron volts if I want. So that's everybody doing solid state physics, you should know this one. Because sometimes you will see that one in nanometers, sometimes you see it in micrometers, sometimes in EV, but immediately you should try to see that. Is that capable? So now if you look at simple solar radiation, so sun is a black body, so it emits all the light, right? So if you look at your solar spectrum, so at the atmosphere, before it comes to, suppose this is your, before it comes to the atmosphere, if you measure before coming to the atmosphere, so that shows that kind of, this exactly that curve, right? Blackbody radiation. But once it is in the atmosphere, you will say, what do you expect? That radiation, you will have absorption, right? Especially ozone, right? So that's why, yeah, so much concern about ozone. So the ozone will absorb a lot of UV radiation, right? So that's why you will see all these dips coming. That's because of the absorption. Here, these are mostly due to water and CO2. These, without, before it comes to the atmosphere, they are pretty smooth curve, right? When it's in the atmosphere, you have absorption coming from water, CO2, then ozone. Ozone is mostly in the UV range. You can see a lot of ozone absorption happening here. It's at a lower wavelength means higher frequency, that means in the UV range, right? So this is mostly the visible range, right? So we have like 400 to 700 to 800. So that's what. If you are working in the solar cells or something, so where do you want to catch the solar radiation? Mostly you like to catch this region, right? That's where the highest energy is. But if you take silicon, silicon is the best solar cell available, right? Silicon has the band gap is about 1.1 eV. So that means if in lambda, what is that number? So lambda is 1.24 divided by 1.1 in micrometers, right? So this is about little over, this is in micrometers, in nanometers 1200 or something, right? It's somewhere here, right? So, but that is not the place you have the highest intensity. So still silicon is the best solar cell we have so far, right? But still it doesn't capture the highest energy. That's why people are now trying to do this something called the tandem solar cells, right? So one solar cell can catch the radiation at this range, then you can have second solar cell to capture energy from this range. That's how the tandem solar cells work. So then you can get much higher efficiency, right? So right now they are only getting, this is where you need to really, but that is mostly in the ultraviolet range, right? So below 400 range. So this solar spectrum is very important for you to know, right? Here. So please have some idea. So if you look at the eye spectral sensitivity, this is how it looks like. The eye is more sensitive to light around this green region. So, and also mostly in the visible range, but mostly in the blue-green, yellow-green range. That's the spectral, spectral spectrum. Okay, so we talked about the Einstein's postulate. So he had these photons with no mass, right? So it has energy this much. So H, everybody should know this number. H is given by 6.63 times 10 to the power minus 4 joules second. So then, yeah, so it has the speed of light. So then this is where the photoelectric effect comes in. Everybody familiar with the photoelectric effect? What does that mean? If you have so some material, if you shine photons, so according to Einstein, this has energy of h nu, right? So then people have already observed some electrons are coming out of the material, right? So if you, I don't want to get to the band structure. So that means, so this energy, he had to assume this photon energy, right? So then what happens? This energy is giving you this electron coming with this highest kinetic energy. So we call the kinetic maximum, right? So these are the ones, we'll talk about the Fermi energy and things like that later. So then first, before it comes out, it has to get free. So that we call the work function, right? So we call the work function. First you need to make sure you are, I think, overcoming that, the interaction to the metal. So that's the work function. Once it is over, so the extra energy is used for the kinetic energy, right? This is what the photoelectric effect. So this also, this is the quantum aspect, right? So this photon, Einstein wasn't very supportive of the quantum mechanics, but he had to use the idea of this photons, right? So the first Max Planck came up with the photons idea, but Einstein used that idea to explain the photoelectric effect. So another important thing Einstein showed was this, the energy of this outcoming, this kinetic energy here, it doesn't depend on the intensity of this light. Suppose I have one wavelength, say red wavelength. I have some this energy, kinetic energy of outcoming electrons, right? So if I increase the intensity, that means I put more energy, but the same wavelength, it doesn't change the kinetic energy. So that means that energy only depends on the frequency, not on the intensity. That's the important thing. Your photo current can increase because you have more flux, right? We call the photon flux. So, but the energy only depends on the frequency. Red light will have smaller energy, UV light will have high energy, right? So that's the important thing. So that's the photon flux. But photoelectric effect, this kinetic, maximum kinetic energy does not depend on intensity. It only depends on the frequency. Yeah, this is what I was talking about, the special theory of relativity. This equation everybody should remember. But I have made a mistake. Actually, this, I like to call this one M0. M0 is the rest mass. So that means if you have the kinetic energy of any relativistic particle, kinetic energy is actually is the this M0 we call M. M is the mass when it is at certain speed, right? So this mc squared minus m0 c squared. So m is really m0 divided by v squared dou c squared, right? Times c squared minus m c squared. That's the kinetic energy. This is the total energy that contains both the kinetic part and the rest energy. This is the rest energy. So you can see now if you use non-relativistic case, what you get? V is very small, right? So then I can expand this one. This is more like 1 minus x squared square root of 1, right? This I can write as 1 minus, this actually minus 1 over. So that means 1 minus x squared minus half, right? So that means I can write as 1 minus this one become plus half x squared, right? So then you have 1 minus this one. So then they cancel, you get only, if you take this one, mc squared, you get this half becomes 2, then x squared becomes v squared over c squared. So you can see now c squared cancel, you get half mc v squared. That's correct, right? That's the classical energy. So anyway, these are details, but everybody should know how to do that. Okay, I don't want to get too much. So this is, we already talked about that. Okay. So next, I want to talk about the wave-particle duality. This is very important. So to explain certain things, if you take even light or even electrons, sometimes you have to consider that one as a particle. For example, for this photoelectric field, the photons are actually more like it's a particle nature, right? So, but if you want to explain some this interference kind of thing, then you have to assume the electron to be a wave. So this is something very puzzling, but it's considered as some standard way to explain some phenomena. So that means your electron waves can be thought of as particles or considered as a wave. So if it is a particle, that means you have to have a mass, right? So that's why we introduce something called the de Broglie wavelength, right? So that means if I write your momentum, you can write this one as simply P is h over lambda. This lambda is called a de Broglie wavelength. So, but also we consider this one as a massive particle, has a mass, so that means you can write this one as mv, right? So that's basically, so then energies always we write as h nu, so that means you can write whatever we want h. If it is c over lambda, so then lambda you can write as h over p, so whatever, all these equations you can make the connection, right? So here, this is what that. Then if you want to write the kinetic energy, in classically we write kinetic energy as either half mv squared or p squared over 2m. In this case, you can write p as basically here p squared you can write as h squared over p squared, h squared over lambda squared, right? 2m lambda squared. So if lambda is 2 pi over lambda, k, so k is 2 pi over lambda, this one you can write as k squared over 2m. H cross means h over 2 pi, right? So if you put that one, this is something you will see many times when we do the solid state physics. So actually people experimentally demonstrated the wave particle nature. So when you start some electrons, so electrons we want to see whether they are behaving as waves, right? if it is a wave, what do you expect? For light, people have seen this interference pattern, right? So if you have these slits, if you have coherent light, so they interfere, they get this bright and dark fringes. Now if you do the same experiment with two slits, not with light, electrons. So if you have few electrons, you have on the screen you see something like this. But if you gradually increase your number of electrons coming through each hole, so you see this one, eventually it will start to show this pretty much like that interference pattern, right? You can see that means these are particles, but it gives the interference pattern. That means they behave like waves. So here they are more like particles, right? So this is an elegant way to show the wave particle fluidity. So last thing to show is the Heisenberg uncertainty principle. So he came up with this idea. If you think about your position, and suppose it's some particle that has a momentum, right? And also it has certain position. So if you can determine this exact position x and the momentum, you cannot have both to be exactly perfect or certain measurements. So if you measure one of them with certain certainty, you lose the certainty of x. Other way around, if you can say this is exactly at this position, that means you lose the information about your momentum, right? So that's he wrote in terms of this delta x is the uncertainty of x. So that's how uncertain, because delta x means, if delta x large means, you cannot tell whether it's here or here or here, right? You have larger uncertainty. But if it is like this, my uncertainty is very small. I can say more precisely it is here, right? So if I say my delta x is very small, then my delta v is very large, because that has much higher uncertainty, right? So your delta x is greater than this divided by delta p. So it has to be higher than that value. So that's the uncertainty means. So the more accurate you know the position, the less accurate your momentum is. Same way, if you know more accurately your momentum, then you know less accurately what the position is. You cannot have both precisely true. You can see in this diagram. So this is my real x position. These are more like this, we call the wave packet. So in this one, you can say the position has large uncertainty, right? Because it can be here, 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 or here. So then your frequency has certain uncertainty here. But if you actually in this case, let's look at this one. Here, this one has less certainty because it can be from here to here. So that means your delta x is much larger. Larger means it's more uncertain, right? It can be here or here or here, so you can determine very less accurately. So, but if you take the frequency of that one, or momentum is you can think about the Fourier transform of that, right? So this one has better accuracy, right? The uncertainty is much smaller because this is only in this range. But if you go from here to here, now you can see this one has more certainty, because here everywhere you can have that one, but here you have less your delta x is less now. That means it has higher uncertainty. That means this one will be more, right, compared to this one. So you can see here. So here the position. So you can see this one has higher position has less delta x. That means better accuracy. Then this one has momentum has less accuracy, right? But if you go here, this one has less accuracy, then this one has high accuracy, right? So you can see how it's going. So typically, your uncertainty principle is written as delta x. That's the uncertainty of x. Delta p, this is h cross over 2. So actually you can easily connect this one to energy and time also, delta E and delta T. That you can easily show, right? How do you do that? So we know delta P is given by P. P is given by, your force is given by what? Force is momentum over delta T, right? Change of rate of change of momentum is your force, right? So then your energy is given by force times delta S, right? So that means you can write delta P over delta T. So that is times delta X. What is that? Force times delta X means work. Work means energy, right? So that is more like delta E. So that means delta P delta X is more like delta E times delta T, right? So that means your uncertainty principle, you can either write this way or you can write as delta E times delta T. So what does this mean? If you can determine your time more accurately, your energy will be less accurate, right? Or vice versa. If you can determine your energy more accurately, your time will be more uncertain. So these two everybody should know. Okay. So now next thing is for mostly your information. So in solid-state physics, mostly we are going to solve something called the Schrodinger equation, right? So solving Schrodinger equation for many particle system is impossible. Right? For one particle or two particles, you can do analytically. But if you have more particles, you cannot do. So you have to develop some new techniques, computational techniques and things like that. So let's talk about a little bit the Schrodinger equation. To do that, quantum mechanics is all about operators, right? So if I think about this, mostly we are talking about position, momentum and energy. That's all we need, right? So position, we use this operator x. Momentum, typically we define this operator is minus IH cross, this grad. Are you familiar with this notation?
I think it's all different.
Yeah, so this is basically d over dxi, d over dy, this is partial derivatives, j, d over dc.
It's the derivative.
Yeah, derivative, partial derivatives, so that's what delta. So mostly we are going to talk about these one-dimensional situations, but generally people write like this one for three-dimensional, yeah. But that is basically, you can think about d over dx, that's enough.
No, I'm finding it.
Yeah, you will find that one, yeah. So then you have x operator, p operator, then you have the energy operator. Typically this is given by this time derivative of whatever the function. So actually I can write that one here. Please write down here, this should be IH cross d over dt. Because we are going to talk about in quantum mechanics something called a wave function. So that can define, I think, everything about you need to know. So wave function, typically we write something like psi that has both this spatial and time dependence. So it can, that's why I wrote as a partial. Partial means you consider the other one as a constant, right? Is psi over dx or d psi over dt. So typically we are talking about psi here like that. So but this is the simple derivation. But also we know, if I know the total energy, typically what is the energy? Is total energy is given by potential energy plus kinetic energy, right? So potential energy is say V, some function of a one-dimensional one, or it can be R if you want in three-dimensional. So this is a potential energy, say V x. Kinetic energy is P squared over 2m, right? Half mv squared. V squared, P equals mv. If you put these two, you get kinetic energy as P squared over 2m. So now if you write this one Vx, what is P? P is h cross over I or minus I h cross. So if you square that one, I squared is minus 1, right? So then you get h squared over 2m, because I have 2m here. Then I have the second derivative of this one, right? D squared over dx squared. That is what my total energy, that's what I wrote here. This is the potential energy, please remember, this is not the potential. You get, also I get negative value here, right? Because I squared is minus 1. So that's what this operators means. So then this is the last thing we are going to talk about, the Schrodinger's equation. Schrodinger equation says if you apply this operator, this still operate, right? We are going to operate this one, operate on a wave function. So wave function is something that can describe everything about your electron or your whatever the quantity, right? So if I do that one, you get this minus h squared over 2m times d squared over dx squared in one dimension. I operate on this psi, it can have x and t dependence. Then I have plus vx, then I operate that on this psi x equals E. E is basically IH cross d psi over dt. Again, this is also has both, psi has dependence of x and t. This is called the time dependent Schrodinger equation, because this has both x and t dependence. But in this class, we are not going to talk about t dependence. We like to do, but that is a little more complicated. It's important here because t dependence tells you how the system evolves with time, right? But we are mostly looking at some static equilibrium situation. So in a more advanced solid state physics, you need to know this one. Actually, that's what in MD simulations people do, right? With the time, they want to see how the system evolves. But they don't use the quantum, it's mostly this classical fields, right? So that is the typical Schrodinger equation. Here I just wrote for three-dimensional case. Don't worry about this grad square means for your information. So grad square means d squared over dx squared plus dy squared of I j plus k d squared over dc squared. That's basically grad square means. So then we are psi, this is the wave function tells you about is both spatial and time. So you can see, so then this psi is basically is a function of your x and t. So then there's a very important quantity called the probability density or probability. So that is basically tells you what is the probability of finding that particle at a given, say, volume here. So that means you need to find the probability is given by, actually that's something we have to, the probability is given as the psi star psi. Please remember, psi is a complex number. complex quantity. You are familiar with complex numbers, right? If you have C as X plus this, like in engineering they use J. We usually use I, it doesn't matter. So then the C star means it's a conjugate of this one. That means X minus JY. This, wherever J, it becomes minus. So that means C times C star means if you multiply you get X squared then plus Y squared, right? That's basically. So here if I have the probability, then if I take the probability over this volume for the entire volume, that means if you look everywhere, you will definitely find your particle, right, somewhere. That means if you take this psi star psi for the entire volume, integrate over entire volume, what should this be? 1, right? So you will definitely find the particle in that, within that volume. That's what this one is. This is in one-dimensional case is dx, but in three-dimensional that should be. So this is basically we are doing from minus infinity to infinity. Please remember that one. Also, this everything, if you take psi out, we call this part as a Hamiltonian. So you might hear this one. So if I take this, see what I have is minus h squared over 2m z squared plus v times psi, right, equals ih squared d psi over dt. This whole thing is called H, is an operator. It's called the Hamiltonian. That means Schrodinger equation you can write as H psi equals E psi. Oh, IH cross, yeah, in this case, in E psi, in the, we'll just write it as this way, IH cross E psi over. So this H means this operator, this plus this one. You guys, this is, you have seen millions times, right?
Oh yeah, we were drowned in this.
What's that?
We were drowned in this.
Yeah. So now since this wave function has both psi and x and t dependence, because psi has both x dependence and t dependence in one dimension, we can write this one separate into some quantity that has only x dependence and do something, they use similar something that has only t dependence. So then you can plug into this one, that equation h, this one is, you can see, if you take t derivative, this doesn't have any t derivative, right? So you can take that one out, then you get this one. So then if you take the d squared over dx squared, this is a constant, right? That's the partial derivative means you take other one. So then you have only this one coming here. So you get this equation. Then divide everything by this one. Then if you do that one, you will see there's one part that has only x dependence, there's the other part that has only t dependence. So that we use as some constant, say E. So then you get two equations. If you have any question, come and see me, I will explain to you. Yeah. So that means you get two equations. This is one coming from only the time dependence part. So this is a simple equation. If you do this one, you know how to do this. You have this IH cross d psi over dt equals E psi. So if you do this one, you can see d psi over psi equals E over IH cross dt. Now if you integrate this one, what is this one? Logarithmic, right? This is simply log psi. So this is YH cross. This becomes simply T. So then if you take exponential, you get up. It's very simple to do that. You can get this relationship by taking the exponential term. But then important thing is this one, only the spatial dependence, not the time dependence. This is the only thing we are going to discuss in this class. How for different systems, the position dependence of your wave function. We are not going to talk about that one. So maybe in the most advanced solid state physics we will do that, but in this class mostly we are going to talk about this. So again you can see in this one, if V has very complicated form, it's impossible to solve. Right? So mostly to begin with this class, we assume this V to be 0. Then it's very simple, right? That's what we call the free electron model. So then this solution is very straightforward. So you can see that this is the equation we will be using. Now this psi has only position dependence, no time dependence. Also this one also we'll do in one-dimensional case. In that case, what is your equation? It's basically minus h squared over 2m d squared psi over d x squared equals E psi. You know how to solve this one. That's very simple. This is second order differential equation. Very simple. The solution is basically some sine kx plus b cosine kx kind of solution. This the whole class is about how to look at these kind of solutions. We are not going to go into this time dependence part. Okay, so now when you do this one, sometimes we have to talk about these coordinate systems, because everybody is familiar with the rectilinear coordinates, right? Typically we have your x, y, z systems. So typically we have x, y, z, right? That's everybody familiar. But sometimes depending on the symmetry, for example, if I use an atom with electrons and all, what is the symmetry? Sphere, right? So then we have to use something called the spherical coordinate system. So in that case, we have your typically this is spherical symmetry. Suppose it has some kind of spherical symmetry. You have to have this. You have this something called r. Then we have this theta. Then if you project this one, we have this angle phi. So typically we define this one r theta, this phi. So I think you should be familiar. So then you can write this one in terms of x, y, z. What is x? X is basically this one, right? In the x direction. That is basically, this is r means this is r sine theta, because this is 90, right? This is r sine theta. Then this length will be r sine theta cosine phi. R sine theta cosine phi. Then what is this y? This is y, right? This one, that is r sine theta sine phi. Then this is your c, that is basically r cosine theta. This is how you write the spherical coordinate system. Then if you want the cylindrical coordinate systems, sometimes your system may have a cylindrical symmetry, right? So in that case, suppose you have some kind of cylindrical, suppose this is your point. So basically we define this one in terms of this one, now your r. So then you have this one, then you have again phi here. So then you have this c. Basically you write r, phi and c. That you can, this is much easier to write because this is R now, right? This your X is now R cosine phi, Y is R sine phi, then basically C, right? That's everybody should keep familiar with these things. We don't use this one too much, but better to have some idea. So, like I said, this is the only equation we will be using. Okay. So, if you want to use for spherical coordinate, this one is going to be really complicated. Like this is how that if you use all these things, you can get this one. So this is in spherical coordinates. This is in rectilinear coordinate system. In spherical coordinates, that can be like this. If you have to use this one, I will give you all this information. You don't have to memorize. So this is the potential, or simple Coulomb potential, right? 1 over R. So solving this one also pretty complicated, right? People have done this one. That's how they derive the energy states for hydrogen atom and all, just by solving this equation. It's not that bad because this has only 1 over R dependence, right? So here some of the quantization examples. So I'll show you 3 examples. One is simply potential well. That means you this Schrodinger equation, your potential is 1, 0. So if you use this equation, this minus h squared over 2m d squared psi over dx squared, then this v term is 0. So equals simply e times psi. If you do this one, you will see d squared psi over dx squared equals minus 2m e over h squared psi. Everybody remember this equation, right? This is more like k squared. So if you do this one, you will get this solution here. So if you do that one, you will find for different states, you get the energies. Your energy is given by some n squared. So if you do this one, you can easily show this one has n squared dependence. So it's very simple to show this one because this k e is what here 2m e over h squared is your k squared, right? So then e is h bar squared over 2m for different is n here. So then you can see these states because the energy is changing as n squared. That's why this spacing is going to get more and more, right? Because n equals 1, then next one n squared. So next one is like 1 to the power 2, then 2 to the power 2, then 3 to the power 2. That's why you can see this separation is getting bigger and bigger, right? But if you take a simple harmonic oscillator, if you have something like this, then your energy is simply, your potential is half k squared. So it's not 0. If you do that one, you get energies E going like n. Very simple to show that one. You can see n equals 0, n equals 1. But these are, n means your separation is the same. Here, separation is getting square, right? You can see that one. But if you use that spherical coordinate system with potential of 1 over r, like I showed there, that is exactly the hydrogen atom, right? If you take hydrogen atom, you have a nucleus that has a proton, then you have electron. So if this is R, what is the potential energy for this electron? Basically, the 1 over 4 pi epsilon 0 is charge divided by your R, right, radius. So that is the potential. If you plug in here, so then you get this one, then that one. So if you solve this one, you have 3 coordinates, r, θ and phi, right? So then we can separate this one, what your solution is going to be. What's the time? I only need 5 more minutes to finish this one. It's almost time, right? So give me 2 more minutes. So if you solve for hydrogen atom, so this your wave function actually has r, θ and phi, right? That's the spherical coordinates. So you can do this one for something called r that has only r dependence. Then you have this y that has θ and phi dependence. So we call this a spherical harmonics, right? So this is the radial dependence that has only r dependence. So important thing is, so this one gives you some quantity n. So that defines something called this principal quantum numbers. If you take energy states, we know they have these orbitals like k, l, m, like orbitals. So each orbital has this sub shells, right? So typically we call these principal quantum numbers coming from this n. So we have n equals 1, n equals 2, n equals 3. So this means your k shell, right? So this means your L shell, M, like that. So then to get L is actually typically, so n minus 1 L states you have. So that means if I have k equals 2, your L can be only 1 and 0. Because n minus 1, k equals 2 means n equals 2, right? Then you have 1 and 0. If you have, sorry, not k. So I talk about L. L equals 2. If I have k equals 1, what do you have? K equals 1 means L has only 0. So if I have k, so this n equals 1, yeah. N equals 1 means k shell, right? N equals 2 means that's a L shell, then my L will be 1 and 0. If I have M shell, N equals 3, that is M shell means I have L equals what? 2, 1 and 0. So then if I have L, I have this M quantum number. So that is, M is going from minus L to plus L. That means if I have L, this one has only 1, right? But if you have 1, it can go from minus 1, 0 and 1. If I have L equals 2, that can go from minus 2, minus 1, 0, 1 and 2, like that. So also you can see that energy goes something like this. Your E is going like minus 13.6 divided by n squared, 1 over n squared. Potential well had n squared dependence, right? E. Simple harmonic oscillator had E is something like n. But hydrogen atom, this is your potential, right? 1 over R. This has energy is going like 1 over n squared. You can see how n equals 1, then n equals 2. It's getting 1 over n squared is getting smaller and smaller. You can see, give me one example. If you take M shell, how many electrons you have? From the high school chemistry, M shell means you have 18 electrons, right? 2, 8, 18. So how do you get 18? M equals 3 means you have, sorry, n equals 3 means your L is 2, 1 and 0. If you have 2, then you have minus 2, minus 1, 0, 1 and 2. This means you have minus 1, 0 and 1. This one has only 0, right? So now each electron can have spin up and down, right? So that means this one will give you 2, this one give you 2, this one give you 2, 2, this one give you 2. That means you have 2, 4, 6, 8, 10, right? How about here? 2 from up and down, 2 here, then you get 6, right? Here, this one electron you can have up and down just 2. Then you have 10, 16, 12, 18, right? So like that you can see how the orbitals are filled. Please work on that one. So this is just the introduction, right? So we are going to talk about, maybe I need, yeah. So from next class I will start about the crystalline solids. So maybe this is something for you to remind yourself. I'll talk a little bit about the Fourier transforms, maybe 5 minutes, then we'll start the next class. Is that clear for everybody? For you guys, it's like a review, right? Yeah. Okay, sounds good. So I'll see you Thursday. So then we'll start the real class, the crystal structures and everything. If you have something you don't understand, come and see me. Yeah.
Thank you.
Yeah. It's good, so maybe one day I can use this.
Sure, please. That's
So
a multi-benefit.
Jayanti and Lance, we were talking about this one, we were thinking maybe we can archive these.
Sure, yeah, no, I'll put it all together for you at the qualifiers.
Yeah, that will be helpful for me.
Sure.
Yeah. If I miss a class, I can upload
Sure.
this one.
My gift to the department.
Yeah, that would be great, yeah.